By now we know how to derive the best orientation for our module. However, we did not yet consider the environment surrounding the PV system. Indeed, in this video we are going to see the possible causes of module shading and how we can determine their influences. Always, when you have to design a PV system, you have to make a landscape survey to find the best spot for your modules. There exist different methods, but we will focus solely on horizon catching in order to obtain the shading factor. Obviously, solar panels work best when there is no shade casted upon them. In fact, a shadow cast on even just part of one solar panel in your solar array can potentially compromise the output of the whole system. Partial shading may be caused by trees, buildings, other objects present in the surroundings of the PV system, or even other rows of the PV system itself. It is also important to take into account the smoke pipes on the roofs, which actually are really problematic to handle because the shade of the pipe is dynamic throughout the day and even the year. So in that respect, it is really important to align in different ways the modules in order to kick in or not the usage of bypass diodes, as we will see in the next chapter. Not only objects close to the system may cause partial shading, but also faraway hills or mountains may obstruct the direct sun irradiance falling on the modules. Hence, during the design, it is important to evaluate the impact of each possible source of shading for all months of the year. This is the task of a PV system installer, and you should be able to tell you if shading will be a problem by using a range of mapping tools. One of these tools is called a fisheye lens, but there are several hardware options available in the market for making a landscape survey. Such lenses can catch the entire horizon. Then, the digital picture is processed for determining eventual shading given by the surroundings of a location. Based on this shading determination, we can derive the optimal irradiance or annual energy yield. In these pictures, the hardware to catch the horizon includes a small metal dome that catches an image from 360 degrees around the horizon. On top of it, there is a pole where a digital camera is mounted. Then, of course, there is a shading disc to prevent direct light from the sun hitting the sensor of the camera. Certain software is then used to analyze the picture and to determine the incident solar energy, sunshine duration, and the real sun exposure. Basically, the software opens the picture and superposes on it the analemmas of the sun for every hour during the year. In this respect, for example, you can see that on December 22nd, which is the lowest spot traced by the sun in the sky, the sun is hidden behind the mountain from dawn until 10 in the morning. Therefore, the modules will not receive direct irradiance in that interval time. So, it is important that you understand that the shading source not always is something that you can see, like a tree or a building next to you, but it can also be something very far away. In this example at the TU-Delft campus, we picked and placed points on the edges of all the objects visible in the sky dome. Actually, for the sake of precision, also trees should be considered, but it is a bit tricky to highlight them with this method. Then, based on the area described by those points, it is possible to find the so-called shading factor, which is simply a number that varies between 0 and 1, which is a function of the time. When the sun is behind the building, the shading factor is around 0 because no direct irradiance is falling on the PV modules, but only diffuse and albedo components. On the other hand, when no object is between the sun and the modules, the shading factor is 1. In general, it should be realized a different diagram for each day of the year. So, for example, in this case, between midnight and 11 in the morning, there is no light, and thus the shading factor is 0. Then, all of a sudden, the sun appears from behind the buildings, and the shading factor reaches its maximum values equal to 1. The shading factor allows to derate the direct normal irradiance by simply multiplying these values each other. Basically, the direct component, which can be usually derived by multiplying the direct normal irradiance times the cosine of the angle of incidence, has to be further multiplied times the shading factor of a specific moment of the day. With this approach, both the dome and the camera should be as much as possible parallel to the ground in order to capture the view from it. On the other hand, If the PV system has to be installed on a tilted surface with respect to the ground, then other methods based on computer optical modeling or LIDAR data have to be employed. In this video, we have seen a method to estimate the shading on our PV modules that is caused by external objects such as buildings, trees, and even faraway mountains. It is based on making a picture of the entire horizon and post-process it with specific software. The output is the shading factor, which is a time-dependent variable that goes from 0 when the module is completely shaded to 1 when no shadow is cast on the module. This value is used to derate the normal irradiance, thus correcting the direct component of irradiance falling on the module.